Welcome and good evening for this talk tonight. We have P.F Patel-Schneider with a talk, Does the Semantic Graphs community care about semantics? What is that stream that you just opened? Well, it's part of our talk series on knowledge graph research, where we've had a few talks already. They are on our YouTube page, and there are more coming up. And today we have Peter, who received this with a 10-year award in 2013. You can check our page for more talks to come. What is this cost action? Well, it's a cost action that is a European research network with more than 30 countries represented. We organize workshops, hackathons, short-term scientific missions. It will run until September of this year. It's headed by myself and Axel Polleres, and we operate some working groups led by Michel de Montier, Remzi Celebi, Andreas Hart, Antoine Zimmermann, Olaf Hartig, and John McCrae, Anastasia Dimou, and Stefan Gostovic are also part of the leadership. Today we have Peter, and I would like to hand over to Olaf for the introduction, and then we will go straight to your talk. Peter.
Thanks, Tobias. So yes, it's my great pleasure to welcome P.F Patel-Schneider to our talk series. Peter has been part of the Semantic Web community since its beginning. He has received his PhD from Toronto University many years ago. Throughout his career, he has been mainly in industry research labs, for instance, at Bell, at Nuance, at Samsung, and recently at SPARQL. His research is in the area of large-scale knowledge representation, and he has also made contributions to standardization efforts at the W3C, most notably for the web ontology language OWL, as well as for the Semantic Web rule language SWIL, and then, of course, also for RDF. Last year, Peter retired, but this doesn't prevent him from still being active. So he's still active, for instance, in the RDF Star working group that's currently going on. And in his bio, he states that his current life goal is to put Wikidata on a firm semantic foundation. So I'm really looking forward to hearing about that and about his thoughts about the semantic graph community.
Thank you, Olaf. And let me share my desktop, actually. I'm sharing my desktop because I'm going to be presenting and off my presentation and also off of a couple web pages. So I'm sharing the whole desktop. So as Olaf said, I'm going to talk about my feelings about the lack of care with regard to semantics that I see in the semantic graphs community. Now, I've actually been careful to use sort of not use standard terminology because I'm going to have to define some of it as we go along. So you'll see how this happens later on. So we have the abstract, which you should have already seen, and the bio, which Olaf forced me to give you. As Olaf said, I recently retired. I used to joke to my colleagues at people who used to work at Bell Labs, who then went to Google, that my post-retirement goal was to fix the Google Knowledge Graph. But my contacts with the people at the Google Knowledge Graph, they got fired in one of the Google retrenchments. So I've decided to switch my efforts to something slightly easier and instead fix Wikidata in my retirement. I don't know if I'll get finished with this. I don't even know if I can get started. Part of the problem with doing things with Wikidata is figuring out how to start. But anyway, that's going to keep me busy at least for the rest of my life, I believe. So Olaf asked me to give this talk because I got this award for the 10-year best paper, 10-year, whatever it is, right? The paper was actually quite technical and talked about the last little bit of semantic foundations for OWL and how that can be hooked into the large amount of semantic work that's been associated with description logics. given the technical and incremental and sort of I-dotting and T-crossing nature of the talk, I wasn't sure I wanted to talk about that effort at all. So instead, I'm going to talk about what I view as the problem with semantics and tools and how users interact with graph-based representation formalisms. And I'm going to try and cut that down a little bit so I can be somewhat more precise. But this is not really a technical talk, although it's going to mention a lot of some technical issues. So here's my thesis. The semantic graphs community doesn't really care enough about semantics. But hey, I've spent a large part of my professional life working on semantics that are related to semantic graphs or knowledge graphs or span networks or whatever you want to call them these days. And here is some of the work I've been involved with. Almost all of this. You can see some of it's general stuff, some of it's standard stuff, particularly W3C stuff. Some of it is related to Wikidata, and there's lots and lots more. These are just a few that I picked out. And I emphasize the standard stuff because it's not just that semantics has been an academic pursuit in this discipline. It's actually had quite a large impact on the standards that people use. And I think that's a good thing. But nonetheless, if you're a user of RDF systems and you have an endpoint that's giving you queries against some RDF graph that's got an ontology in it. So in the simple RDFS ontology, where you have instance and subclass, and you want to find out the instances of some class, it just seems correct to write this simple query, select something, where something, and instance RDF type class. And that's it. You should expect to get all the instances of all the classes from this query. Not some of them, but all of them. But instead, what people write is this second query, this more complicated query, where you have a SPARQL path query with you combine RDF type and then any number of RDFS subclass of links. Why is this? Why do we have to do this? I claim it's because people don't care about semantics when they give us when they give us endpoints or systems that we can retrieve information from. And so my claim is that anybody who's had to do this, has had to create these more complicated queries, has suffered from a lack of care with regards to semantics in the semantic graph community. And the reason that we have to do this is that in many cases, the tools that we use to access RDF graphs, particularly large RDF graphs, and particularly large RDF graphs that are at public endpoints, just don't abide by the semantics of RDF and RDFS. And this is a simple accommodation and one that I generally know enough to put in all the time. But it is an accommodation and it is annoying every time I have to do it. And I'm not a great typer, so there's a significant number of syntactically incorrect queries that I put against these systems that are syntactically incorrect just because I had to add these extra character strokes. And every time I do that, it really bugs me. So what can we do? Well, that's not really the point of this. Well, I guess it is really the point of the talk, right? But let's leave that till the end. First, dive deeper into the problem. Before we get into the real problem, I have to define my terms. And I specifically use semantic graph because it's not the common name for the things that we query against the web. The common names are either linked data or labeled property graphs or RDF graphs or knowledge graphs, right? So I want to change the target slightly. And I also have to define what I mean by semantics. And maybe my definition of semantics that's used here will be quite surprising to you. So what is a semantic graph? Well, as far as I'm concerned, well, it's an explicit representation of information about the world, which at least some notion of meaning, i.e., it's not, you're not querying it just to get back bits. You're querying it to get back facts about the world. And it uses some variation of edges in a graph. And it might be a labeled graph or directed graph or multi-graph or a hypergraph or and I was searching for the word for a graph that allows edges as nodes, and I couldn't come up with it. I think there is one for that, but you know, graphs that allow edges as nodes. And strangely enough, although the idea of graphs was graph-based representation was because you could view them, actual graphical representation of the information isn't really all that important. What's important is that you have nodes and edges and links, and the information is stored in representation to these edges and nodes and labels. So the second thing that I'm going to require of semantic graphs is it's not just data, shall we say. There's some sort of notions for structuring and organizing information, right? And generally that means that the semantic graph supports the creation of ontologies. There's other things that you might want besides ontologies, but let's stick to ontologies for now. And as you know, there's lots and lots of formalisms that's used in the graph representation community for doing that. So in RDF, we have RDF type and RDF subclass, and OWL, or in RDFS++, we have OWL same as, we have OWL class definitions. We have these weird numbered things, which are what's used in Wikidata for these things. Other graph-based formalisms have similar ontological primitives, shall we call them. And the third thing that I'm going to require the third thing that I want to look at are systems where the ontologies are represented in the same manner as the other information, i.e., RDF type is in no way special, or WD:P31 is in no way special. So as you'll see, this kind of rules out OWL, at least OWL as a description logic, but not OWL as in RDF. So I'm going to require this. And why am I going to require this? Well, because I think that this is one of the things that contributes to the problems that I see with lack of care with respect to semantics. So I think there's quite a few systems, tools, endpoints, large repositories that fit, right? So pretty much every RDF graph that has RDF content in it, including ones that have OWL content in them, as long as the OWL content is expressed as RDF edges. So, and that includes, you know, DBpedia is an example, lots of other services that provide SPARQL or similar access to an RDF graph. But doesn't have to be RDF based, right? I mean, Wikidata, I think, fits this notion of a semantic graph exactly. Similarly, Psych does. Similarly, I'm not going to talk much about Psych anymore because it's kind of a closed system and it's no longer freely available. Freebase was one. The Google Knowledge Graph and other commercial knowledge graphs, probably. I've kind of made it a point not to understand too much about these, but it's from what I understand, they could be considered as semantic graphs. I'm going to exclude a couple of things. I'm going to exclude description logics per se, and I'm going to exclude schema.org. And the reason I'm doing that is because their ontology is separated from the data. And then finally, what about labeled property graphs? Every time I look at them, I come up with a different answer, whether I would consider them to be semantic graphs. And today, I guess I'm sort of leaning towards that they're not semantic graphs because they really don't have much of an ontology. And even if you look at the schema stuff that gets added on top, I still don't know if they have much of an ontology, right? So let's say that I'm still a bit undecided whether to include them, but I don't think it's important for the purposes of this of my thesis. So here's an example, right? A very simple RDFS semantic graph with only 5 triples in it that talks about this resource atoms that has a type, has a various other things. And we can see that the ontological information looks a lot like the other information. Now, it turns out that this is RDF, so there's a notion of namespaces, and the ontological information is kind of in a different namespace, but that's not really important. It's still really using edge labels just like any other edge label, and properties just like any other property. So I say that, this is a semantic graph, admittedly an absurdly tiny, trivial one, but it's going to be enough to show the problems. And I'm going to use some small examples and some large examples. So let's go back to Wikidata. I think a lot of people on this call will know a lot about Wikidata, but not everybody. So Wikidata is a large collection of statements about the world that underneath it forms a node labeled, edge labeled multigraph that allows edges as nodes. That's pretty much what the formalism underlying Wikidata is. It's somewhat more complicated than that, but that's close enough. So it fits so far, the semantic graph things. Nodes and edges have meanings. Information isn't organized via an ontology, and the ontology relationships use the same facility as the domain dependent relationships. And we can see that if we go into one interface against Wikidata. Here's the Wikidata page for Douglas Adams. Doesn't really look like a graph here yet, but it really is. This is a node, and everything in Wikidata is numbered. So this is Q42. Wikidata is into it's not really a pun, very bad numerical references. So here we have Douglas Adams. He is an instance of human. Well, that sure sounds ontological to me. And if you notice, there's nothing special about this thing. It's just a name like anything else. He's got spouse is way down here. Spouse is way down here. There. He has a spouse. And here we have the start time and end time, which are annotations. So we can use this spouse Jane, Douglas Adams spouse Jane Benson edge and stick other stuff on it. This interface doesn't look very graphical, but as I said, it really is a graph underneath. And if we go around and we look at human, we can see now human is Q5. I don't think there's a numerical reason for Q5, except that 5 is a small number. And we see we have subclass of and other things, and subclass of. So it looks a lot like RDFS, except in using slightly different names, and somewhat the expressive power is somewhat different. So I claim that Wikidata definitely fits the semantic graph definition, and it better because I put the definition together to include Wikidata. And the other thing about Wikidata is that there actually is a mapping into RDF, and you can see, and when you map some of the information on Douglas Adams' page, you get this information, and you see these strange numbers in there, and they don't matter. Wikidata, well, we won't go into that. And there's a public endpoint, and we can actually retrieve right queries using SPARQL against this, using some other weird stuff. And I think a lot of you have probably seen this, and we can find out that there are 223 cats. Okay, so let's just take a quick second to look at this query, because this is actually this is kind of the primary example of how to query Wikidata. We are asking for items and their labels. That's their names, essentially. And the item has to be related to cat via instance of. That's the query. And there are lots and lots of examples of queries related to Wikidata that look like this, where we want to find the instances of some class. We just do this query. So I hope I've indicated that there's at least some large semantic graphs that are available that are useful. Wikidata is one, DBpedia is one, Psych is sort of one. And therefore, as long as we're ignoring the fact that we might all be steamrollered by the ascendancy of non-symbolic AI, that semantic graphs are important. We should care about them, not just me and you, but a community should care about them. An important community should care about them, because they are a good way of representing and exploiting world information, and even more particular, a good way of sharing world information. So I'm claiming this is not simply an academic exercise. It's something that's related to something that's useful. So just to recycle back to description logics and schema.org, why did I exclude them? Well, because the ontology in these two is kind of conceptually separate from the data. You don't get this mixing, and therefore, particularly for description logics, you get tools that have to use the ontology information and have to exploit it in ways that are different from the actual data. So you tend to end up with different kinds of tools than for tools that are related to what I'm calling semantic graphs. Now, you can map either of them into RDF in particular. And once it's in RDF, you can use standard RDF tools, and then you would have a semantic graph. But I'm not going to consider these as semantic graphs per se. And I don't think that doesn't harm my thesis. I'm just restricting the set of things slightly. So if the problem exists in this smaller set, then it will exist in part of the bigger set. So far, that's semantic graphs. And now let's flip to semantics. I don't know, anybody who cares about semantics has been confronted with the problem of justifying why they care about it, right? And so I tend to justify the need for semantics by saying it's an independent specification of what should happen. And if it's a good semantics, then it's something that reasonably well-educated people can look up and say, yeah, that seems right. Okay. And you can say, that if the results of your system match what the semantics says, then in some sense they're correct. And it's certainly much better, more satisfying notion of correctness than just retrieve the edges. And then once you've got that, then you can actually build tools that do them, and the semantics then becomes an independent verification that the tool is correct. Now, so far, so good. I am not limiting myself to to formal semantics here. I'm claiming that this whole thesis of mine is relevant for both systems that have formal semantics and systems that have informal semantics. So what's the difference? Well, here's a formal semantics. There's lots of works for formal semantics. The yellow stuff on the right is an extract from the RDFS semantic conditions in the RDF semantics W3C recommendation. And what's important here is that some otherwise normal tokens, let's see if I can find one. Oh, okay, here we go. Yeah, RDFS subproperty of here. It's kind of hard to see, it's pretty small. They crammed this all in one slide. Actually has semantic conditions placed upon it so that wherever it appears, this semantic condition should be the case. Right? And so in this case, that subproperty of is transitive and reflexive. Or an actually more important one, where is it? Right, so here's the one. So if we look at, whoops, I can't highlight here. If we look at this third from the bottom one, this is the relationship between anyway, relationship between type and subclass. Yeah, I think so. So there's a notion in the RDFS semantics that type and subclass are related. And if you're asking, for instance, that something subclass is important as well. But lots of systems don't have this level of formality. If any of you have interacted with Psych, there really isn't a full, formal, official specification of the semantics of Psych that I'm aware of anyway. And if anybody's involved with Wikidata, you'll know that there is no formal specification of what Wikidata is supposed to be. Instead, we get things like this. Here is part of the page for Wikidata subclass of, which is, as you expect, the equivalent of RDFS : subclass of. And here is several phrases, two phrases, that tell you what the meaning of subclass of should be. Now, it's completely informal, but nonetheless, I'm going to claim that if we're going to be using Wikidata, we really should believe this, right? And why should we believe this? Well, because subclass, all properties are equal in Wikidata, but some properties are more equal than others. And this is one of the ones that's very much more equal than the other properties, because it is used to create the ontology and is used to structure information in Wikidata. So both formal and informal semantics counts as far as I'm concerned. So actually, there's one thing that occurs to me that I have not quite defined, and that's the semantic graphs community. And I think I'm just going to define that as anybody who interacts with semantic graphs in whatever way possible. So here we are, back to the thesis. Now that we've got our definitions out of the way. And the thesis is the semantic graphs community does not care enough about semantics, as evidenced by common accesses that produce results that are incorrect with respect to the formal or informal semantics underlying a semantic graph. And here's an example, back to our subclass of example. Suppose we load this 3-triple graph into an RDF SPARQL system and query it with a query that I think should produce the right answers. In many cases, I think in the vast majority of them, unless we've done something special, right, we will likely only get one answer, that Adams is an instance of human. That will be the only type relationship we get of that, instead of the, no, it's not really, actually, it's not correct 3. How many answers should we get out of this query? I guess more than 3. So 3 is not even correct, but we should at least get that Adams is a mammal and an animal. We probably also get that other things, quite a few other things, but let's say we're definitely missing things about Adams. And to get the correct result, what do we have to do? Well, we have to go for this more complicated query. And that's an added cost. But so the rejoinder here has got to be something like, well, complex query isn't all that much more complex, and it's an annoyance, but it's just an annoyance. So quit complaining, right? And moreover, that everyone knows how to construct a more complex query. Well, and here's evidence A to the contrary. Here's an official query against Wikidata where you should be doing this more complex kind of query that doesn't. So this query is going to potentially miss instances of cats if the more complex query is the one that's required, right? So although experts in the system may think everybody knows that they have to construct the more complex query, it's not the case. New people may not know. They may not read the documentation carefully enough to know. And in any case, it's a barrier for usage. So it's even if everybody currently knows how to do it, you don't really want to add this extra burden. So I claim that even this very simple case is a problem. But things are quite a bit worse. So I know when I write queries, I write these more complex ones. But here's a case of subproperty, right? So if father and mother are subproperties of parent, and we have this graph where my parents are listed as my father and mother, which is only appropriate, I think, and I query it with parent, I'm not going to get any answers in most cases. Instead of the correct 2. The required query is actually a fairly complex query. We have to search for all the subproperties of parent and use that variable in the property position, using the results of that subquery in the property position of another triple. And fewer people, myself in particular, are likely to remember to use this required query here. Why is that? Well, it turns out that in many cases, you get the right answers, even with the simpler query. And writing the more complicated query is difficult and may actually be much slower, because it has the second query has a variable in the property position of a triple, and there are SPARQL systems that run slower with these kinds of queries. But nonetheless, the middle query, which I've used a lot, and I assume anybody here who has used SPARQL to query a semantic graph has used, is dangerous, because even though it produces the right answers today, it may produce the wrong answers tomorrow. And so somehow we put ourselves in this position of routinely writing dangerous queries. Let's go back to this subclass case, right? So subclass and subproperty interact with each other. So even this more complicated query, where here we're asking for instances of Olympic class ocean liner, is inadequate, because there might be subproperties of type or subproperties of subclass, right? And it turns out that it is provable that there is no SPARQL query that will retrieve all instances of a class in an RDFS knowledge base unless the RDFS consequences are somehow otherwise materialized. Right. And there's a bunch of ways of doing that. There's actually standards for that, but they tend not to get used very much. And there are tools that do it correctly. But in general, we write lots of class-based queries that are inadequate, and there's just no way of fixing the problem. So, are we sunk? Well, it turns out that there's not many cases where you get the wrong answers. This is actually one. This one actually does show up in Wikidata. So Wikidata is actually kind of a torture test for these sorts of things, because it does use things like subproperties of RDF type and subproperties of RDFS subclass. So it's actually a case where these things do matter. But you don't have to go for subclass and subproperty. You can have things like inverses, right? So if we have a case where parent and child are inverses of each other, this query is inadequate, right? Unless the system is somehow doing the right thing for us, but lots of systems don't. And so we get the wrong answers. And it gets even worse. So RDFS has domain and range constructs that can result in missing types. And that was the first example. I myself didn't add these extra types in. RDFS++ has other things. And certainly OWL has lots of constructs that produce consequences. And if we have a semantic graph that has OWL class content in it, we have to have we cannot just query it with standard SPARQL querying. But nonetheless, people write OWL content and put it out, and people expect to be able to query it using SPARQL. So let's do one last example here. But so far, everything has been so far all the examples have been RDFS or RDFS++. Here's an example which even goes beyond OWL. So Wikidata has got a lot of stuff in it. It's even got this notion of, is meta class for? What is meta class for? Let me bring up an example. So here is ship type. What is ship type? Well, ship type is a class of ship types. So it's a second order class. You can see second order class. It also states that it is a meta class for ship. What does that mean? It means that every instance of ship type are subclasses of ship. So here we have ship type is meta class for ship. So every instance of ship type should be a subclass of ship. And so the second and the third triples there imply the last. This is quite sophisticated modeling. But nonetheless, it gets used quite a lot in Wikidata. It gets used for ships, it gets used for products, it gets used for lots of manufactured things. It's very common. And it's actually powerful and it's useful. It's actually quite useful in Wikidata. But there's nothing in Wikidata that enforces this inference. Instead, what happens, and the reason I know this is I got involved in this project that's involved with keeping all the information in Wikidata about ship shape. And there are actually queries that people put together, and I fixed up some of them, that when you run them, and they return, and they return event. There we go. Okay. You find out that the answers to this query are violations of this thing. So in other words, they are things that should be subclasses of ship, but are not. And there's currently 234, and once in a while I go through and take the results of this query and massage it, and then add in the missing information. But it's a pain, right? And there's other examples, right? So I haven't even gotten into open world versus closed world. And I haven't even gotten into another very important one in Wikidata, and also lots of other semantic graphs, restrictive qualifiers. And these are things like saying, we have them for, yes, I believe we have them for Douglas Adams. There's Douglas Adams. So we have in Douglas Adams, find him and his spouse. Okay, so here we have Douglas Adams' spouse is James Belson, and there's this notion of a start time and an end time. So Douglas Adams' spouse was James Belson between 1991 and 2001. Not now, right? And not before. So if we queried for spouses, and particularly if we queried for spouses of some famous person like Elizabeth Taylor, we would get 6 marriages, 5 spouses, I think it is, something like that. None of which are current, of course, because she's dead. Right? She is dead. Yes, she is dead. And so, what do we do about this? Are we supposed to just accept the fact that we have the restrictive qualifiers that may make the results that we get back kind of not correct, or should we do something about it? So that's another place where this lack of concern about semantics can bite us. So far, semantic graphs exist. They have formal or informal semantics that have consequences, and many methods for accessing semantic graphs do not take into account the consequences of the semantics. And this requires extra effort from everyone who needs to access semantic graphs, leads to errors, and sometimes leads to the impossibility of getting the right results. So I think this is bad. And I think this is a problem for us and is caused by by people just not caring about the semantics. I mean, that's wrong. So why do we get these wrong answers? Well, maybe it's just impossible to formulate what we mean by the correct semantics. So far, none of the things I've shown are impossible in its simple semantics. And certainly in informal semantics, you can say anything you want. So they're sort of informal semantics are as adequate as anything humans can put together, i.e. completely inadequate, but we won't go into that. There's another failure mode that essentially when you build a system and you produce API, you let users access it, the accesses you get them just are incorrect. Even though everything else is fine, you could have built a better system, but you didn't. And sometimes it's just that we don't do the right thing. So the users are supposed to understand what the problem is and fix up our queries as we go along. So there's multiple things that could be going wrong. What could we do to make things right? Well, we could just say, well, there's all these problems with semantic graphs. Don't use them, or don't use their ontological components, right? We could say, oh, this is a problem. Let's use better tools, right? And there are some, right? But they're not used as much as they should be. Oh, we could say, well, yeah. I mean, we can't use the better tools because they're too slow or closed source or whatever reason, or take too long, and this is another common one problem. What we'll do instead is we'll fix things up outside of the system a little bit. So what we'll do is essentially, when we create this graph and stick it in a system, we'll write some automatic programs that go through and fix things up. So external programs that look at the content and say, oh, I know the system, the core of the system isn't doing things right. I'll add something else. This turns out is very common in Wikidata. They're called bots, and they actually can do a lot of changes to Wikidata. The problem is they get written by random people outside of the core people who maintain Wikidata, maintain the Wikidata infrastructure. And so there's not much control over exactly what these things do. Or we could do what was done in the ship case, is essentially get people who care about ships to add in the missing information, even though it's actually is implied, to add it in. And I don't like any of these solutions. Well, oops, no, sorry. The only solution I like is better tools, and that's not used as much as I think it should be. The other ones are all problematic in my concern. So, but, you know, again, why has my view of the universe not, why has my correct view of the universe not been widely accepted? I know, life is tough. Well, there's a lot of people who actually don't buy this spiel at all, essentially. You know, who cares about semantics? All we want is the raw data. We're going to feed it to a program and it's going to do something. And as long as the program understands what's going on, then we don't care about any of this semantic stuff. Yeah, never mind. A variation of that is, oh, my program only needs data in this particular area. And in this particular area, the data is all perfectly fine, and I don't need this other stuff, so I don't care. A third problem is that vendors, there's lots of vendors that provide, some vendors, I won't say lots. There's vendors that provide tools that are used for semantic graphs. Some of the vendors are leery about providing tools that actually do abide by semantics. Now, there are some that do, and some that are pretty good that do it. So Allegro Graph has a mode where you can see the consequences, the RDFS consequences of the data you put in. So that's nice, and in my view, it would be nice if people used it a lot more, but lots of places it doesn't get used, right? And then, of course, there's the cost of doing this. Even if you think that Allegro Graph is great and you should use it all the time, will it actually work for Wikidata in this RDFS mode? Well, Wikidata isn't exactly RDFS, but suppose you took Allegro Graph and fixed it up to work for the intended semantics, at least part of the intended semantics of RDFS. Would it actually be able to load all of Wikidata? Wikidata is big. Loading it, even on a fast machine, takes somewhere between hours and days. It gets changed a lot, so you have to be able to update the data as changes come in. There's lots of costs, computational costs in doing it, and of course, there's the cost of actually building the software to do it. So all of these things, I think, are reasons that the problem sits with us. But so how can we try and fix this? Well, I think we better consider the trade-offs. Turns out that I think there's a regrettable lack of forward thinking, in that the cost of adding RDFS subclass of star to your queries is not that big, but it's borne by a lot of people. So why not, instead of having a little pain on everybody, put more pain on the developers, right? And I think that those of us who have the little pain foisted on us should agitate for better tools. But I think that really the answer to this has got to be somebody, somewhere, somehow has to develop an important tool, economically important tool or system that really benefits from semantic aware stuff. And my thought has always been, if neural networks can drive the revolution in computation that we're currently seeing, then maybe some economically important tool that uses semantic graphs could drive some better development of tools, maybe. Anyway, that's the end of my talk, and I guess we have a question and answer session. So who's doing the questions and answering?
Yes, me. First of all, thanks, Peter, for the very interesting talk. We have a technical problem, namely, if I clap, the noise cancelling will eradicate that. So I do it nevertheless. So thanks for the interesting talk. The end came sudden. I particularly have one question to start off the Q&A session, and I would like to ask the audience to put in their questions into the YouTube chat, such that I can address Peter. And there were some coming in already. So let me start with my question, and that is, you had this with the subclass in RDF type, you had the small query and the bigger query with the property path, right?
Yeah.
And when I talk to people who start to apply semantic technologies in their, I don't know, PhD thesis in manufacturing research, for instance, I was told once that when you talk about RDF type, you have to use the longer query and not the shorter one. But they didn't know why. So my question is, isn't the first step kind of awareness in education, such that people understand what's going on and that they actually do query rewriting to get in some desired inferences that could be provided by a better tool in a better world? But yeah, being aware and being educated to know what's going on and what the problem actually is.
Yes, I mean, I think that actually is support for my claim that you can't just say that everybody knows how to write the bigger queries, right? Because they may even if they understand that it's magic, right? They get annoyed because they don't want magic. They want to understand what's going on, right? And you have to tell them, well, the reason you need to do this is because of this system is not doing the right thing, and you have to overcome its problems, right? And of course, that's not a happy thing to say.
Yeah. Good. Let's start with some questions here. Yeah, there's one question. Like part of the solution is the SPARQL 1.1 with entailment regimes. And I guess that is what you didn't mention, but what you actually mean, right? The support of these kinds of standards.
Yes, right. So essentially, they're actually, yes, you're right. There is an official specification of how one should change SPARQL to produce these consequences, right? And of course, that requires tool writers to actually do the legwork underneath, because these entailment regimes, they specify what the answer should be, but not how to do them. And,
Exactly.
and tool implementers have to do the right things. Now, for RDFS, it's not, well, let me rephrase that. For RDFS, there are only minor tricky bits, but for more powerful systems like Wikidata, right, there could be more, right? And of course, the SPARQL 1.1 entailment dreams don't talk about, restrictive qualifiers like temporal qualifiers, what to do then. I mean, it's unclear. I mean, in this case, it's actually unclear what the right answer should be. If you have temporal qualifiers built into your system, what should SPARQL be returning, right?
Right. Okay. There's a question from Axel. Do you want to ask that yourself?
Yeah, sure. So wait, let me just quickly switch on also my video. So thanks, Peter, for the great talk, which in many respects I agree, but as usual, at some points I'm not sure. One thing I wanted to ask was, so that this problem, for instance, if you redefine the type and so on, yeah. So some people call that non-standard use of this reserved vocabulary. So looking back, wasn't that the bad idea from the start, that we started to mix in the vocabulary with the data? So expressing all axioms in RDF itself, expressing basically unary, the instance of the unary predicate in a predicate that is equal to the binary predicate, which allows all kinds of tampering with it. Yeah. So wouldn't a reasonable refresh or so also be restricting the use of this, or maybe just ignoring redefinitions of the vocabulary? What do you think about that?
So I used to be very much of that feeling, right? You should not touch RDF type and RDFS subclass at all, right? I mean, and this is essentially the OWL-DL solution. OWL-DL forbids that, right? But I've kind of come around to a more nuanced viewpoint. Wikidata actually makes very good use of these things, right? Let's take an example from ships again, right? So the Titanic is a ship. It's a steamship, but it has a ship class, which is a Olympic class ship. I mean, there's only two of them, the Olympic and the Titanic. But in ships, it's very common to have a thing called to belong to a class, right? And how should one model that, right? Well, it can make a completely separate relationship, but really the Titanic is an instance of Olympic class ship, right? But nonetheless, we want to call it out specially, right? So we really want to have this relationship vessel class, which is a sub-property of type, right? And that of course, that is messing with type, with the ontological primitives a little bit, but in a nice way. I mean, there's also nasty ways of saying things about these ontological predicates, but this one doesn't seem so bad, right? And the other thing you get from the mixing in thing is things like, oh, we don't know exactly what the ontological primitives are in the beginning, right? We'll let the community kind of come up with some, and as developers, we'll madly scramble behind them as they go along, right? Again, it's not the safe and sane world of description logics. It's more like the messiness of the real world. And I think that one has to at least live partly there, but I think we're much too far in the wild west version of that, where in Wikidata, particularly, people create these ontological properties without any notion of how they interact with the rest of the system and how hard it is to work with, right? And this is metaclass is one. Somebody came up with this notion a few years ago, and it seems to have taken over without anybody understanding really how it should be used or implemented. And that's not great, but it's very powerful, right? So anyway, yeah, the world is messy, representation is messy, right? But at least we have jobs.
Nice conclusion there. There's one question by Paula that I want to reformulate. So part of the tool improvement is to bringing some of the entailment into the SPARQL query processors. And you talked about RDFS entailment. There's also data type entailment, RDF entailment, all things. If you had a wish free, which level would you like all the tools to be?
So yeah, now we're getting into problems of computational complexity, right? I mean,
right.
So this goes back to my wish list for Wikidata, right? Wikidata is this wonderful resource. It's very powerful. And every time I interact with it, I start tearing what's left of my hair out. So my wish is that we would go quite a ways beyond RDFS++, right? In particular, to have things like is meta class 4, right? That's a powerful modeling construct, very useful. In particular, to have things like defined classes. So I didn't go into this at all for Wikidata, but because it's not really quite relevant to this talk, but it turns out that if you ask Wikidata how many women there are, how many women are in Wikidata? The answer at one time was 7, and the answer is supposed to be 0. Why? Because the community has decided one should not create instances of the class woman. Instead, one should create instances of the class human with sex or gender female, right? Now, that's a strictly informal consensus, and every once in a while, every once in a while somebody notices, oh, there are instances of women, usually princesses and fictional characters, right? And goes through and rejiggers the information about these so that there are then 0 instances of women, right? But again, as a newbie, and like me, I consider myself an expert in representation, but I actually expected to get back a decent answer, and I was very surprised at 7, right? And I asked, and somebody says, "Oh, the answer should be 0," and that sort of surprised me even more. So what I would like to see is the ability in a system like Wikidata of having definitions. It's able to say that, oh, if you want the instances of woman, right, then the system will, behind your back, change that into find the instances of human that have sex or gender female. Right? Now, that's going beyond RDFS++ towards OWL for sure. And the question is where to stop, right?
Exactly.
Right. And there are places to stop. Even OWL has places to stop, like OWL RL, right? So OWL RL might be a good place to stop.
Okay. There's a question from Paul, and he asks, he's done some work in the ship domain, and it's super complex. And even if, as you showed, the ship domain is so complex that it takes you to fix Wikidata every now and then, will these semantic graphs ever be able to work for this messy world that we're living in?
So, the ship domain is fairly complex, and it's even worse when you include things that are related to ships, like sailboats. So sailboats are vessels, water capable vessels, and the way you model them is a little bit different than ships, and similarly for boats. So the problem is that there's all these gradations. But as far as I can see, all of the intended meaning for ships, boats, submarines, sailboats, there's quite a few moving pieces, but nonetheless, there's nothing that's really that requires anything more than sort of quasi-linear time to compute, right? It's not like you're trying to do complete OWL DL inference, right? It's like on the OWL RL level, or like the data log level, right? So you're trying to do data log kind of things. And yes, that's computation, but it's not horrendous, right? Except of course, when you're trying to cram whatever it is, 300 million triples into a computer, right? Then it gets to be a problem. But, hey, computers are wonderful, marvelous things. They should be able to, what is it? What's the saying? Think of 7 impossible things before breakfast. So we really should be exploiting these things. And yeah, so yeah, ship is complex and a pain, but it's, I think, doable. And the solutions for ship are not just for ships, but they're for a huge chunk of Wikidata.
Yeah. Okay, there are some comments by Michael coming from a practical perspective, and part of your solution was to maintain materialization, and he said they build it in, it's explosive, there are significant trade-offs, they stop to materialize inverse properties and so on, and sub-properties, limited sub-property use. So some strategies are not practical enough. So do you think that the state of the art in these SPARQL engines has to greatly improve to be practical in terms of entailment?
So there's several things. One is, as soon as you materialize consequences, you have to be able to unmaterialize them, right? When their support goes away. So that's a pain. There are techniques from the description logic community on how to do that effectively, and that so you don't pay too much of a penalty for that. You don't pay too much of a penalty compared to the amount of extra information you have to materialize, right? Now, nothing says you have to treat everything the same way. You might want to materialize inverses, because that really only doubles, at worst doubles, right? But not materialize the subclass things, right? Instead, computing that on the fly, right? So of course, if you have a very large ontology, adding in all of the implied type links and the implied subclass links might be a problem, might blow up something, right? But you don't have to do it that way. You could, at query time, compute these, and it's an engineering trade-off as to what works. And again, part of the deal is that, computer prices and computer power tend to grow, right? And at the moment, of course, we're in this year, the price of computer memory is increasing, but over time it has decreased a lot, right? So, and of course, the speed of computer memory and particularly secondary storage has increased a lot, to the point where it's not that very expensive to be able to put all of Wikidata, even with materialized stuff, into main memory, right? And there are actually systems, the RDFS system from Oxford actually does that. It's designed to work, in systems that have like a terabyte or several terabytes of memory and store everything in main memory. And there are advantages to that, and particularly because materialization and dematerialization can be done quite quickly then, right? So these are all engineering trade-offs that one has to do. And of course, I think that a really big impediment is that to do this well requires smart programmers, and you can't ask ChatGPT to do the programming.
Nice statement there. That is, I think, would be. I don't have more questions from the Q&A, so that was, I think, a nice finishing words for the Q&A session. I would say we cannot have ChatGPT to do all the programming that is required here. With that, thanks again for your answers and your insights. I would then move on to the housekeeping of the talk series, sharing my screen again, if I find the right window. So there we are. That was the talk by P.F Patel-Schneider. Next up, we have Mr. Bollemann on June the 17th. With that, I want to close today's session. Peter, you can stay on the call. Follow us on this thing formerly called Twitter. Find our recordings on our YouTube channel, cite and subscribe.